Good evening and welcome to the free CCNA CyberOps instructor training. It's the 14th of October 2019 and that means it's time for Chapter 5 Network Infrastructure. These videos are brought to you via the Open University Cisco Academy Support Center and the Institute of Coding. I'm very much hoping that we don't get a repeat of what happened in the previous video for the CCNA 2, where I got 10 minutes into the video and everything fell apart. Oh, hi Kieran. Yeah, he seems to be an awful lot better now. They reckon it was just a slight unusual rhythm in the heart, but they've checked it all out and it's all looking good. Yeah. Okay, so we are now on Chapter 5 of the CCNA CyberOps. This is a relatively big chapter, so I won't hang around because there's an awful lot to cover in here. Huge amount of technology we're throwing at you again. So this is quite a deep chapter. This covers network infrastructure. So what I'll do is I'll start straight away. We'll start nice and easy. Network devices. So we have end devices. End devices being things like, for instance, PCs, laptops, servers, printers. An end device is effectively something that initiates a data transmission session or terminates a data transmission session, as opposed to an intermediary device, which is something that data flows through. Okay, and an intermediary device is used to connect together the individual end devices on the network and also to connect multiple individual networks together to form an internetwork. So a typical intermediary device would be a router, which connects networks together, or a LAN switch, which connects hosts together inside a subnet. A multi-layer switch, this is a switch that works at layers above layer 2, so layer 2, 3, potentially layer 4. So we have our intermediary devices, we have our end devices, and of course we have the media as well that actually carries the information. This would be like air copper cables, air fiber optic cables, or air wireless media, in which case it's carried on electromagnetic waves. Routers, one of the most important intermediary devices. The functions of a router are: it provides path determination and packet forwarding. In other words, a router's job is to work out the most efficient path from source to destination and then route the packet along that path. The router is responsible for encapsulating and decapsulating packets. A packet, of course, being what the information is called when it's at the network layer of the OSI layer model, the layer at which routers operate. The routers use a routing table in order to determine the best path to use to send packets to a specified network. Now the routing table is critically important. It contains directly connected routes and also routes to remote networks. The router will search through its routing table for a network address that matches the destination IP address of the packet. So effectively, a router's job is to connect entire networks together, not end devices. Connecting end devices together, that's the job of a switch. So because a router connects entire networks together, in its routing table it will have network addresses. And what it will do is it will search the routing table for a network address that matches the destination IP address of the packet. What we can do is we can take the IP address and we can logically AND it with the subnet mask, and that will automatically generate a network address. If the router has that network address in its routing table, then it will forward the packet or route the packet out of the interface that is connected either directly to that network address or to a router that's on the path to that network address. In other words, like a next hop router to that network address. If the routing table does not have a network address that matches the destination IP address of a packet, it will make use of what's known as a gateway of last resort, if there's one configured, or learned from other routers via dynamic routing protocols. If there is no gateway of last resort configured or learned, then the packet will be discarded. The router has to perform the following three major steps. Number one, it will de-encapsulate the layer 2 frame coming up from the data link layer. It will remove the layer 2 frame header and trailer in order to expose the layer 3 packet. It then examines the destination IP address in the IP packet header in order to find the best path in the routing table. If the router finds a path to that destination, it will then encapsulate the layer 3 packet into a new layer 2 frame and forward that frame out of the exit interface. Now, devices can have layer 3 IPv4 addresses, or for that matter IPv6 addresses, whilst the Ethernet interfaces make use of layer 2 data link addresses. These are the MAC addresses, the media access control addresses, that are burnt into a ROM chip on the network card. The key thing to realize here is when we're routing a packet from a source to a destination across an internetwork consisting of many routers, many hops, the source IP address and the destination IP address, they remain the same. They never change. The source IP address is always the same, the destination IP address is always the same. But the layer 2 addresses, the data link layer addresses, they will change with every hop of the router. Every hop of the packet as it moves from source to destination. Okay, so looking at router operation, primary function of the router is determine the best path to use in order to send packets to each subnet, and in order to determine the best path, the router searches through its routing table for a network address that matches the destination IP address of the packet. The routing table search will result in one of three different path determinations. It will either be a directly connected network, which is one that's literally directly connected to an interface on that router. It will be a remote network, which is a network that we have to get to through another router or series of routers, or there'll be no route determined. If there's no route determined and we have no gateway of last resort, then it will discard the packet. Okay, so the routing table of a router stores the following information. It stores what are known as directly connected routes. These will be shown with a capital C at the front of the line. Remote routes, these will be routes that have either been learnt via a dynamic routing protocol, such as RIP, OSPF, EIGRP, BGP, etc., or possibly configured using a static route. And a remote route will be a network that we have to get to by going via another router. The destination entries in the routing table can be added in several ways. So a local route interface, these are added when an interface is configured and active. So in other words, when we go into the interface, configure an IP address and a subnet mask, and then type no shutdown to bring the interface up, that will automatically configure the local route interface. And a local route interface is represented by a capital L at the start of the line. It will then have the IP address that's actually configured on the interface, followed by a /32 mask, which is known as a host mask. In other words, /32 is 255.255.255.255, and it identifies a single IP address. A directly connected interface, these are added to the routing table, again, when an interface is configured and active. Only these will contain the network address. They'll contain the address to the actual network that that interface connects to. These will be indicated in the routing table with a capital C. Static routes, these are added when a route is manually configured and an exit interface is active. And then finally, dynamic routing protocols, these are added when a routing protocol dynamically learns about the network from another router. Okay, so this might be EIGRP, OSPF, BGP, etc. And these will then show up in the routing table with a code letter which represents, for instance, D for EIGRP, O for OSPF, B for BGP, etc. What I'll do is I'll see if I can't show you approximately what this looks like in Packet Tracer. Okay, so you now see a Packet Tracer network. It's a moderately complicated network, just something I was playing around with a little while ago. We've got VLANs on here, virtual local area networks. We've got a couple of multi-layer switches. We've got a router up here. The multi-layer switches are working as effectively routers. They're actually routing IP packets. If we go into one of these routers and we do let's pick that one there, just have a little look and see what it has in its routing table. Okay, so this is a Cisco 2911 series router. What we'll do is we'll go into the command line interface. We'll type enable, which I can shorten to ENA. This has dropped me into global configuration mode. I can then type show IP route to see the entire routing table. And that's a fairly big routing table. Okay, so let's see if I can actually get all of the information in one screen. There we go. We can see that we've got codes, and these codes indicate either a local interface. This was the /32 mask that we mentioned earlier. This is the IP address on the interface of the router. Directly connected network with a C. This will be where the interface points to a network. We've also got static routes with an S. We've got RIP routes with an R. If we look in our routing table, you'll notice that most of our routes begin with a D. If we look at the code, D stands for EIGRP. So these are routes that have been told or informed to this router using the dynamic routing protocol EIGRP, Enhanced Interior Gateway Routing Protocol. This is where routers are basically exchanging routes with each other to build up their routing table. You can see that we do have some directly connected routes with Cs together with the network address and the subnet mask. This is a point-to-point network. And we also have some Ls, which are our local route interfaces, which will have the IP address that's actually on the interface together with the /32 host mask. Some of these routes are unusual because they're actually external routes. In other words, these are routes that have not been generated in EIGRP, but they've been propagated into EIGRP from some other routing protocol, probably OSPF on this network. If we have a look at one of the other routers, just to compare the routing table on that one, see what we've got in there. Go into privileged exec mode and we'll do show IP route. And we can see that we've got some OSPF routes here. This is another dynamic routing protocol. So these routes were added when the two routers, the neighbouring routers, communicated with this one using the open shortest path first routing protocol. And they show a network that we can get to together with its subnet mask, and also how we can get to that network. We can get via a next hop router, a neighbouring router with an IP address of 172.16.0.1, or via a neighbouring router with an IP address of 172.16.0.5. These are actually our layer 3 switches. Okay, so to get to this 10 network, 20 network, 30, 40, 50 and 60, you'll notice that we can either go via 0.1 or 0.5 every time. 0.1, 0.5. That is because we're sitting on this central router, and to get to those networks we can either go via the switch to the left of the router or via the switch to the right of the router. Okay, and because it costs exactly the same amount going either way, it puts both routes in the routing table. If one of these routes was much faster than the other, it would only put the best route in the routing table. But because they are both exactly the same cost to get there, it puts both routes in the routing table. Okay. So hopefully that'll have given you a little idea of what a routing table looks like. We've got our local route interfaces with the L, they're directly connected with the C. We've got static routes. In fact, that was the only thing we didn't see. Let's see if we've got a static route on here somewhere. I don't actually know whether we've got a static route on here. We might have a static route on this one potentially. Let's have a little look. The static route is where we've manually configured the route. My mouse wants to play up now. It's gone very jittery. Nothing worse than a jittery mouse. Okay. Enable show IP route, which we can shorten slightly. No, there's no static routes on here either, but we can see these OSPF routes. We can see there's an EIGRP route down here. Okay. I mean, you can actually type in show IP route connected, which will only show the connected routes. You can do other things as well, so we can say show IP route OSPF, which will only show the OSPF routes, or EIGRP, which will only show the routes that are learned via EIGRP. That's useful. In fact, I wonder whether, let's have a look. There isn't one for showing local routes, but what we can do is we can use the pipe symbol and say include L space space. See if that'll do it. There we go. So show IP route, we'll pipe that to only include lines that have L in, followed by a couple of spaces, and we can see the local routes as well. So there's a lot of things you can do inside a router. Okay, moving from routers for just a moment, we're looking at some other devices. We've dropped down a layer now. We've dropped down, in fact, potentially 2 layers. We've gone from the network layer where routers live into the data link layer, which is where bridges and switches live, and the physical layer, which is where hubs live. So an Ethernet hub acts as a multi-port repeater. So its job is to receive an incoming electrical signal, and then it will immediately forward a nicely regenerated, boosted, retimed version of that signal. Because an Ethernet cable is made of copper, copper is a good conductor, but it has a resistance. We do get a power loss across the cable. That power loss degrades the signal. The signal starts off as a nice, sharp, strong signal. By the time it gets to the end of an Ethernet cable, maybe 90 meters away, it will have degraded into a rather weak signal. The repeater, or hub, which is a multi-port repeater, will take that rather weak signal and it will amplify it. It will retime it, boost it up, and send it on its way. Okay, hubs use the physical layer, or layer 1, to process and forward the data. They're actually very dumb devices. If a frame comes in one port of a hub, it has absolutely no idea where it should go, so it just sends it out of all the other ports, which can be a problem, because if you're sending a frame out of another port, when a frame's coming into that port, we can have a collision. Okay, so a bridge, which is a better device, this lives at the data link layer, layer 2 of the OSI layer model. A bridge has 2 interfaces, and they are connected between hubs to divide the network into multiple collision domains. Okay, so the bridge makes use of the hardware addresses, the media access control addresses, to intelligently connect 2 network segments together. Well, not network segments, to intelligently connect 2 devices together. Bridges, you don't see bridges very often these days, but what you do see is you do see multi-port bridges, and a multi-port bridge is a switch. So a multi-port repeater is a hub, a multi-port bridge is a switch. And the great thing with a switch is it's got a lot of ports on it. And that means that we can connect multiple devices together intelligently, because like bridges, the switch segments the LAN into separate collision domains, one collision domain for each port. The switch makes forwarding decisions based upon the MAC address. So for instance, if we go back to our packet tracer again for just a moment, we have a switch here. It's an access layer switch. If we go into that switch and see if we can have a little look at the MAC address table. And how do we see the MAC address table? Super easy. Go into privilege mode by typing enable. We can shorten that to ENA, and then we'll just type show MAC address table. Okay, I have one entry on my MAC address table. That is on interface gigabit 01. I can see the MAC address of a device on that interface. That is almost certainly the router, because the router is plugged in to interface gigabit 01. If I ping something from this PC here, we should see a second MAC address appear in the routing table. Who am I going to ping? I'll ping this PC over here in VLAN 10. That's 192.168.10.1. Bring up the command prompt and ping 192.168.10.1. Now, what I probably should have done is type ipconfig to make sure I've got an IP configuration on that device, but it should have, because I actually hovered over it and I could have sworn I saw an IP configuration on it. Not that you can hover over PCs in real life, you'd actually have to go into the command line and type ipconfig. You'll notice we dropped a couple of packets. That was while it was doing an ARP request, looking for the default gateway. It now has that ARP entry in the ARP cache. So if we were to do that command again, the ping again, all 4 packets would go through. What we're going to do now is we're going to go into the switch, and what we should see is not one entry in the MAC address table, we should see 2 entries in the MAC address table. Okay, so what a switch does is it makes forwarding decisions based on Ethernet MAC addresses. It looks at the frame as it comes into the switch, and it looks at the source MAC address in that frame as it enters the switch. It goes into what's known as the ingress port, and it makes a note of that source MAC address together with the port that it entered the switch on, and that's how it builds the MAC address table. So MAC address tables are built using the source MAC address and the port that they entered the switch on. Once the MAC address table is built, when a frame comes into that switch, it can look at the destination MAC address, check that MAC address against the MAC address table, and if there's an entry, it can then switch the frame to the correct egress port or exit port. Wonderfully clever things, switches. Okay, now if we look at switching operation, now this is basically going to say exactly what I've just said. So the switch will learn by examining the source MAC address of a frame as it enters the port. It will add that MAC address to the MAC address table, tying it in with the port that it came in on. If we send a frame into a switch and that destination MAC address is not in the MAC address table, then it basically has to flood that unicast frame out of all the other ports on the switch. So effectively, until the MAC address table is built, the switch acts very much like a hub. In fact, it acts exactly like a hub. It will take the frame in and it will have to flood the frame out of all of the other ports on the switch until the MAC address table is built. Once the MAC address table is built, it can start using intelligence, and it can forward the frames based on the entries in the MAC address table. VLANs, Virtual Local Area Networks. What a VLAN does is it segments a network based upon multiple factors. These could be function, project team, application, the floor in the building, all kinds of things. It creates separate logical broadcast domains, and these broadcast domains can span multiple physical LAN segments. So in other words, we can have a VLAN 2, which is the IT VLAN, and this can come off of separate switches on first floor, second floor and third floor, can all have ports in VLAN 2, ports in VLAN 3 and ports in VLAN 4. And even though they're on physically separate switches, only connected together via a trunk link, only the PCs in VLAN 2 can communicate with each other, only the PCs in VLAN 3 can communicate with each other, and only the PCs in VLAN 4 can communicate with each other. If we need to have communication between VLANs, then what we need to do is we need to have a trunk link coming off of the switch and going up to a layer 3 device, such as a router, potentially a layer 3 switch. And that layer 3 device is capable of connecting together the different VLANs. A layer 2 device cannot do that. So effectively, when we put VLANs on a switch, what we do is we logically group together the ports that are in that VLAN. Only the ports in that VLAN can communicate with each other unless we have a trunk link going up to a layer 3 device such as a router, which can then connect the separate VLANs together. So if I had a switch, for instance, and it was an 8-port switch, in fact I've got an 8-port switch. We have a little look. The now quite famous Cisco 3560 layer 3 power over Ethernet, passively called 8-port switch. What we've got here is we've got 8 fast Ethernet ports. By default, all of those ports are in VLAN 1. This means that if we plug PCs via Ethernet cables into these ports and we put them all in the same IP subnet, they will be able to ping each other. However, what we could do is we could take 4 of these ports and put them in VLAN 10, the other 4 ports in VLAN 20, and then only the PCs that were in the same VLAN would be able to ping each other, unless we somehow or other took the information up to a layer 3 device such as a router or a layer 3 switch. Now this is a layer 3 switch, so we could do some fancy stuff with this. We could create what are called switch virtual interfaces, and we could put IP addresses on the switch virtual interfaces and get it to route that way. So a VLAN is a very powerful way of segmenting a network. It creates logical broadcast domains that can span multiple physical LAN segments. It improves network performance by separating a large broadcast domain into smaller ones. So just as a switch, a standard switch, could separate a large collision domain into small collision domains, in fact, on a switch, what you ideally wish to do is you wish to run full duplex on all of the ports with only a single end device on each port. If you have a single end device on each port, you can run full duplex on the port, you can run full duplex on the network interface card, and in that way each individual port on the switch would be its own collision domain. It's known as microsegmentation. You have a 24-port switch, you'd have 24 collision domains. Each collision domain with only one device in. Being able to run full duplex, they can't have collisions. If you did this with a hub, you would have one big collision domain with 24 devices all in the same collision domain, which is a total mess. With VLANs, it gives us the ability to do the same thing but with broadcast domains. Using VLANs, we can break down a big broadcast domain with multiple devices in into lots of smaller broadcast domains with less devices in, which is far more efficient. Also, having VLANs prevents users on different VLANs from snooping each other's traffic. Okay, moving on to spanning tree protocol. Spanning tree protocol is designed to ensure a single logical pathway between all the destinations on a network by blocking redundant paths. This prevents loops by strategically blocking certain ports. It makes use of what's known as a bridge protocol data unit frame in order to prevent these loops. As you can see in the diagram, we do actually have a loop between switches S1, S2 and S3. Frames could potentially go around this loop forever. And the problem is with a frame, because it lives at layer 2, the data link layer, inside the frame header, there's nothing to stop the frame from going around and around a loop forever. If we move up to the next layer, the network layer, and we look inside an IP packet header, there is a field called the TTL field. That stands for the time to live. And the time to live field is an 8-bit number. Let's just say it's set to 64. And every time that packet goes through a router, that number is decreased by 1. So by the time it's gone through 64 routers, the TTL field drops to 0, and the next router will drop the frame. So thanks to the TTL field, packets can't really go round loops forever. But the problem is at layer 2, there is no such thing as a TTL field in the frame header, so a frame could potentially go around this loop forever. So what happens is the switch will work out a way of blocking one of the ports. Now I don't think this is going to go deep into exactly how it does that, because that's quite an explanation of how the bridge protocol units and the bridge identifiers and things like that and the priorities actually work. But what it will do is it will block one port in order to eliminate a loop. And if, for instance, the link between switch 1 and switch 2 now failed, it would be able to bring the link between switch 2 and switch 3 back online in order to allow for continuous transmission. So spanning tree protocol prevents loops by strategically blocking ports, and it uses bridge protocol data unit frames in order to prevent loops. Excellent. It might even be possible to, let's have a little look. Yeah, what I've got running here is I've got spanning tree, I've got Wireshark running, and Wireshark is actually connected to the switch via that cable. And what we can see is we can see all kinds of traffic, including spanning tree protocol traffic. We can see the bridge protocol data units. Okay, so there's spanning tree actually running on a real switch. Multilayer switching. Now a multi-layer switch supports what are known as routed ports. These are switch ports on which we can actually configure an IP address. So these are switch ports that are working at layer 3 of the OSI layer model. We can configure an IP address on them. Multi-layer switches also support switch virtual interfaces, or SVIs. These are logical ports. They only exist in software. They're not actual physical ports like routed ports are. They're known as VLAN interfaces. So we can create interface VLAN 100, which is a switch virtual interface, and we can put an IP address on that, and that could be then used to forward frames based on layer 3 information. A routed port is a physical port that acts like the interface on a router. It's not associated with any VLANs, whereas an SVI is a virtual interface, only exists in software, and it can be configured for any VLAN within a multi-layer switch. So I might just possibly be able to show you what they look like. Let's see if we can do this. We go back to a packet tracer. We do actually have 2 multi-layer switches. So if I go into one of the multi-layer switches, and we'd have a little look around and see what we can see. The multi-layer switch is configured with many things, but if we look at the VLANs, we'll do a show VLAN brief, and we can see that we actually have a sales VLAN, HR VLAN, IT VLAN, Fred, Bob and Joe VLAN. I think I was running out of names there for the VLANs. We've got the VLAN numbers 10, 20, 30, 40, 50, 60, sales, HR, IT, Fred, Bob and Joe. And if we do a show IP interface brief, you will see that we actually have switched virtual interfaces for those VLANs. These are logical interfaces. They only exist in software. However, we're able to put IP addresses on them, and they can be used to route traffic at layer 3. This is a multi-layer switch. This is doing the job of a router. In fact, this even has a routing protocol running on it, I believe. Okay, this multi-layer switch is running OSPF, and it is routing various networks. So these are networks that are being told to its neighbours via the OSPF routing protocol, and those neighbours are then able to add those networks to their routing tables. Okay. Starting to get quite deep now into the networking, aren't we? Right. Wireless communication. WLANs, wireless local area networks. They make use of radio frequencies, electromagnetic waves. Radio frequencies normally at one of two frequencies, 2.4 GHz or 5 GHz. And they use those instead of cables at the physical layer and the MAC sublayer of the data link layer. Clients connect to the network via a wireless access point, which is effectively a wireless version of a hub or a wireless router instead of the Ethernet switch. So with 802.3, which is a wired Ethernet LAN, we make use of a cable. With 802.11, which is a wireless LAN, we make use of radio frequencies. 802.3 Ethernet LANs, because they're on a cable, we can make use of what's known as collision detection, or to give it its full term, carrier sense multiple access collision detection. We can detect a collision on a wire because it shows up as a slightly unusually higher voltage, and then the information can be retransmitted. With wireless, we can't detect a collision, so what we have to do is we have to avoid the collision in the first place, and it does this by making use of RTS and CTS signals, request to send and clear to send signals. Availability, wired LAN, we need to have a cable connection. Wireless LAN, anybody with a radio network interface card or a wireless network interface card in range of the access point. Signal interference on a wired network is relatively light. In fact, if it's using fiber optic cable, it's almost nothing. Signal interference on a wireless network can be considerable. However, modern modulation standards can actually reduce the impact of that. Regulation, the Institute of Electrical and Electronic Engineers standards for the IEEE 802.3 wired Ethernet LANs, and for the wireless LANs it's regulated by all kinds of standards, including the Federal Communications Committee in the US and various others. Wireless network operation. The wireless client will associate with a wireless access point, and then it will authenticate with that access point. So, well, in fact, the way it works is it authenticates with the access point first, then it associates with the access point. Configurable wireless parameters include the network mode. When we talk about the network mode, we're talking about, are we using IEEE 802.11b, G, N, AC, that type of thing. The SSID, that's the service set identifier, which is basically the wireless name. So this is the name you have given your wireless network. The channel settings, which will determine the frequency. Depending on the different countries, you have different number of channels. Depending on the different type of network mode, you have different numbers of channels. So for instance, with 802.11g in the US, you have 11 channels. In the UK, you have 13 channels, and I think in Japan you have 15 channels. There will be 3 non-overlapping channels. This allows you to cover an area. Security modes and encryption and passwords. So for instance, are we going to be using WAP? Are we going to be using WEP? Or are we going to be using WPA? So WEP is wide equivalent privacy. It's very easily broken. There is software on the Kali Linux distribution known as Aircrack NG, which can break a WEP encrypted wireless access point in very short time. WPA is much stronger, and WPA2 is extremely strong. Okay. Wireless devices must discover and connect to a wireless access point or wireless router. The IEEE 802.11 standard was originally developed with two authentication mechanisms. This was open authentication, which provided wireless connectivity to any network device, and shared key authentication, which is based on a key that's pre-shared between the client and the access point. Okay, so the client to access point association process. The wireless client goes through a three-stage process in order to associate with the wireless access point. Discovery, which is where the wireless client locates the access point to associate. The access points tend to send off what are known as beacon frames. Authentication, which is where the wireless client sends out an authentication frame to the access point. The access point then responds with a challenge text. The client encrypts the message using its shared key and returns the encrypted text back to the access point. The access point then decrypts the encrypted text with its shared key. Of course, if it can decrypt the encrypted text, then the shared keys match. Okay, so that's good. And then finally, association. This is where the wireless client forwards an association request frame that includes its own MAC address. The access point will respond with an association response, including the access point's MAC address. The access point then maps to a logical port to the wireless client. You wouldn't think there was so much going on, would you, with a wireless access point? Okay, wireless access point devices. We actually have the access point itself. So on a small network, this is usually a wireless router. So it integrates the function of a router with the wireless access point. On a large network, there can be many access points which allow us to basically roam from one access point to the next. We can also make use of what's known as a wireless LAN controller, WLC. This controls and manages the function of access points on a network, so it's a centralized controller. It simplifies the configuration and monitoring of numerous access points. So that works in conjunction with what's known as a LWAP, or a lightweight access point. Lightweight access points are not controlled individually. They are actually centrally managed by the wireless LAN controller, so they cannot any longer act autonomously. Firewalls. So we now move on to firewalls. Some common firewall properties. Firewalls have to be resistant to network attacks. All traffic should flow through the firewall, providing of course it's permitted, and the firewalls enforce access control policies. There are several benefits of using a firewall on a network. So they prevent the exposure of sensitive hosts, resources and applications to untrusted users. They sanitize protocol flow. They block malicious traffic from servers and clients, and they reduce security management complexity. However, firewalls also prevent some limitations. So a misconfigured firewall can have very serious consequences on the network. There's been quite a few occasions where we've had problems on networks where it's come down to the fact that somebody has configured a firewall with an access control list that has blocked some critical traffic. The data from many applications cannot be passed over firewalls securely. Users search for ways around firewalls and there are indeed ways around simpler types of firewalls, such as the packet firewalls, the ones that do packet inspection, standard packet inspection. Network performance can be slowed down by a firewall because of course it's actually got to process the traffic, and unauthorized traffic can indeed be tunneled as legitimate traffic through a firewall. It does depend on the type of firewall though. So a packet filtering firewall or a stateless firewall, these are usually part of the router and they permit or deny traffic based on either layer 3, well generally it is layer 3 and layer 4 information. So in other words, on IP addresses and port numbers, TCP, UDP port numbers. And those types of firewalls are relatively easy to get round. A stateful firewall, this allows or blocks traffic based on a state, a port or a protocol, and it monitors all activity from the opening of a connection until it's closed. These are a lot more solid. Application gateway firewalls, also known as proxy firewalls, these are capable of filtering information at layers 3, 4, 5 and 7 of the OSI layer model. So that's the network layer, the transport layer, the session layer and the application layer. Very impressive. Host-based firewalls, either server and personal firewalls, this is software that's actually on the PC, like for instance the Windows Defender firewall that you find on Windows PCs. A transparent firewall, this filters IP traffic between a pair of bridged interfaces, and a hybrid firewall is a combination of different firewall types. Okay, so a packet filtering firewall, very common. This is normally configured actually on a router using what are known as access control lists, and these will permit or deny traffic based on layer 3 IP addressing information and layer 4 TCP port numbers. TCP port numbers of course identify which application that information should be sent to. These are stateless firewalls, and they use a simple policy table lookup that filters traffic based on specific criteria. And it is possible to get round these things, especially if you send information via non-standard ports. So for instance, if you're trying to get SSH working and port 22 is blocked, you can set your SSH server up to run on port 443 because you know that port 443 is not blocked on the firewall. And a simple packet filtering firewall will just look at the port number and say that's 443, I guess that's HTTPS traffic, and let it through, whereas in fact inside it's SSH traffic. A stateful firewall is a lot more powerful. These are the most versatile and common firewall technologies in use. They provide stateful packet filtering by using connection information maintained in a state table. They are classified as network layer, but they can also analyze traffic at layer 4, the transport layer, and layer 5, the session layer. Very powerful firewalls. We have our next generation of firewalls. In the picture you've got some of Cisco's ASA, Adaptive Security Appliance firewalls. These provide standard firewall capabilities like, for instance, stateful inspection, but they also contain integrated intrusion prevention. They can make use of application awareness to control and block risky applications. They've also got upgrade paths built in to include future information feeds, and they can implement techniques to address evolving security threats. These are very powerful devices. Intrusion prevention and detection devices. I think, as I said in an earlier video, an intrusion detection system is a little bit like a guard dog with no teeth. It makes an awful lot of noise. It basically allows everybody to know that there's a problem. It sends an alarm off, but it can't really do anything about it. Whereas an intrusion prevention system is like a guard dog with titanium teeth. So not only does he bark and let everybody know that there's a problem, but he also removes the burglar's legs. So a intrusion prevention system is an active device, and it can actually do something about the attack, whereas an intrusion detection system can really just warn you. Characteristics of IDSs and IPSs. Both of the technologies are deployed as sensors. They both make use of signatures, and you can update the signature files on IDS and IPS systems relatively easily in order to detect patterns of misuse in network traffic. They can also detect what's known as an atomic pattern, which is a single packet, or a composite pattern, which is a multiple packet signature. Advantages and disadvantages of IDSs and IPSs. The IDS is good in one way because it has no impact on the network. So there's no real problems with latency or jitter. Latency is a delay. The jitter is a variable delay. where you've got a varying delay between packets. Jitter is actually more dangerous than latency, especially for voice traffic. There's no impact, network impact, if there's a sensor failure, and there's no network impact if there's a sensor overload. Whereas with IPSs, advantages are they can actually stop trigger packets. So a packet that triggers an alarm can actually be stopped, and they can make use of what's known as stream normalization techniques. Disadvantages of IPSs: the response action cannot stop a trigger packet, so it can give you a warning, but it can't really do a great deal about it. You need to make sure that you have correct tuning required for the response actions, and they're more vulnerable to network security evasion techniques. With an IPS, the sensor issues might affect network traffic. Also, sensor overloading can impact on network traffic, and in some networks we can have some impact on the network in the form of latency, in other words delay, or jitter, variable delay. We've got host-based IPSs. This is software installed on the system. We've also got network-based IPSs. So these are dedicated or non-dedicated intrusion prevention system devices. Okay, I'm going to have to speed up a little bit, otherwise we're going to run out of time. Cisco have some specialized equipment. They have their advanced malware protection or AMP system. They also have their web security appliance and cloud web security appliances, and the Cisco email security appliance or ESA. I let you have a look at that in the chapter. Traffic control with access control lists. Okay, an access control list is a series of commands that control whether a device either forwards or drops a packet, permits or denies a packet, based on information that's found inside the packet header. They're very handy. They can be used to limit network traffic in order to increase network performance. They can provide traffic flow control. They can also provide a basic level of security for network access. They can filter traffic based on traffic type, and they can also be used to screen hosts to permit or deny access to network services. The access control list is effectively a list. It's a sequence of lines known as access control entries. These lines are either a permit or a deny action, and then some form of match statement. If the packet matches the match statement, it will either look at the permit or the deny, and if it's a permit, it'll allow it to go through. If it's a deny, it'll drop it. The lines are read sequentially, so you do have to be very careful of the order of access control entries in an access control list. Okay, so Cisco, we've got two types of IPv4 access control lists. We have the standard and the extended. The standard access control list, this can be used to permit or deny traffic based on only the source IPv4 address, whilst the extended access control list can filter IPv4 packet based on the protocol type, the source IP address, the destination IP address, the source TCP or UDP ports, the destination TCP or UDP ports, and optional protocol type information. So they give you much finer, more granular control with an extended access control list. The standard and extended access control list can be created either using a number or using a name. The name is a more flexible way of doing it. And we can also get an access control list message generated and logged when traffic meets either the permit or the deny criteria. SNMP, Simple Network Management Protocol. This allows administrators to manage end devices such as servers, workstations, routers, switches, and security appliances. It consists of three elements. It consists of a manager. This runs the SNMP management software. An agent or agents, which are nodes that are being monitored and managed. And what's known as the MIB, or the Management Information Base. This is a database on the agent that stores data and operational statistics about the device. So the agent is the managed node. This will have a MIB on it, which is a database that stores data and operational statistics about that device, and SNMP will then talk back to the manager, which basically runs the SNMP management software. One of the nice things with SNMP is you can have read access or read-only access, but you can also have write access. Now you have to be very, very careful with your permissions and your passwords for write access, because it's completely possible to push configurations to actually control networking devices using SNMP. So you need to make sure that your read-write SNMP community string, or password in other words, is a nice, strong, secure one. NetFlow. NetFlow is a Cisco technology, and it provides statistics on the packets flowing through a Cisco router or a multi-layer switch. This is handy because it provides data to enable network and security monitoring, network planning, traffic analysis, IP protocol accounting, and even for billing purposes. It makes use of a NetFlow collector and with analyzing software, and a NetFlow enabled device, like for instance the NetFlow enabled router in this slide. Port mirroring. This is a clever technology. On a switch, unicast frames will normally only flow between the two ports that are part of that communication session. So if I've got a PC and I'm trying to communicate with the default gateway, then the frame will literally go from my port that my PC is plugged into to the default gateway's port that the router is plugged into, and any PCs plugged into any other ports on that switch will not see that unicast traffic, because the switch creates a little virtual circuit between those two ports. This is normally a very, very good thing. It's good for performance, and it's also good for network security, because anybody plugging into another port on the switch can't see your traffic. However, if you wish to monitor traffic for legitimate reasons, it's nice to be able to set up what's known as port mirroring. This is a feature that allows the switch to make duplicate copies of traffic passing through the switch, and then send that data out of a port which has a network monitor attached. It's done on a Cisco switch using what's known as SPAN, Switch Port Analyzer mode. You create a SPAN source session and a SPAN destination session. Okay. Syslog. Syslog is the most common method of accessing system messages, and it allows networking devices to send their system messages across a network to a Syslog server. Syslog logging is a service which provides three primary functions. It's there to gather login information for monitoring and troubleshooting, to select the type of logging information that's captured, and to specify the destination of captured Syslog messages. NTP, this is Network Time Protocol. It runs over UDP at the transport layer on port 123. This allows routers on a network to synchronize their time settings with an NTP server, and these use strata levels, so it's a hierarchical system. NTP can be used to synchronize to a private master clock, or it can synchronize to a publicly available NTP server on the internet. The NTP servers are arranged in these levels, known as strata. A strata 0 is a super high precision timekeeping device assumed to be accurate with very little or no delay. These can, for instance, be the big atomic clocks, the big cesium atomic clocks. You don't normally set your system up to synchronize to a stratum 0 NTP server. You would normally synchronize to a lower stratum server. So stratum 1 is connected to the authoritative time source, and these act as primary network time standards. It's perfectly acceptable to synchronize to a stratum 1 server. And stratum 2 or lower, these are just connected to the stratum 1 devices through network connections, and then they will synchronize their time using NTP packets from the stratum 1 servers. Why would you do this? It's extremely important to make sure that you have accurate time on all of your networking infrastructure devices and your servers and even your workstations, because if somebody breaks into your system and they cause some damage, and you log it, you log their IP address, where they've come from, what they've done, and your time is wrong, then unfortunately that information will be absolutely no use whatsoever to law enforcement. If the time is incorrect, the information is invalid. You must make sure, for logging purposes, that the time is correct on all your network infrastructure devices and your servers. Okay, AAA, authentication, authorization and accountability. Authentication, who are you? Normally via a username and a password. Authorization, what are you allowed to do? And accounting, what have you done? Typical AAA servers would be, for instance, Radius, the Remote Access Dial-In User System, or Cisco's TACACS, Terminal Access Controller Access Control System. If you've ever been to a hotel and you've logged into a wireless access point, you'll notice that you can log into the wireless access point normally without requiring a username or a password or anything like that. But as soon as you log into the wireless access point, you get a little portal pop up that asks for a username, a password, your room number, etc. That's normally running off of a Radius server. A VPN, it's a virtual private network. This is a private network that's created over a public network. Effectively, you create a encrypted tunnel, a VPN tunnel, from one VPN endpoint to another VPN endpoint, and any traffic that travels across that encrypted tunnel is safe. So you could have a remote worker on one VPN endpoint, you could have the head office on another VPN endpoint. It will create an encrypted tunnel between those two VPN endpoints, and any traffic that's sent across that tunnel is safe. So the VPN is private, and it will keep the traffic inside the encrypted tunnel totally confidential. IPsec is a service which allows for authentication, integrity, access control and confidentiality. Confidentiality is normally done via encryption, and integrity is done via hashing. Okay, network components, typical overview now, very quickly. Two LANs connected together via an internetwork. We have end devices, we have intermediary devices in the form of switches. The internetwork, we've got some routers. We have the devices themselves, which is the hardware. We have the media, which is the cabling, or in the case of wireless, electromagnetic waves. And we have the services, which is the software that runs on top. Services such as DNS, DHCP, FTP, web services, email services, etc. Physical and logical topologies. Physical topology refers to the physical connections. It actually identifies how the end devices and infrastructure devices are connected together, literally how they're wired together. A logical topology refers to the way the network transfers frames from one node to another. Okay, so this is more related to the addressing that's used, specifically the IP addressing. WAN topologies, we have point-to-point topologies, a permanent link between two endpoints. We have the hub and spoke topology, where we have a central hub, the central office, and then branch offices at the spokes. We have a mesh topology. In the diagram we have a full mesh topology. This is extremely resilient. If there's a failure of a link, there's always another way of getting there. However, it's very expensive to use a full mesh topology. LAN topologies, we have the star topology, where end devices are connected to a central intermediate device, normally going to be a switch. We have the extended star, where additional Ethernet switches interconnect other star topologies. We have the bus topology, which is where all the systems are chained together and on a central backbone bus, which is terminated at each end. This was the old 10 base 2 and 10 base 5 networks, very rarely seen these days. We have a ring topology, which is where end devices are connected to their respective neighbours, forming a ring. Unlike the bus topology, the ring does not need to be terminated. This would be, for instance, like token ring, IEEE 802.5, or FDDI, Fiber Distributed Data Interface, which can have either a single ring or a double ring. Neither of which are used a great deal these days. Most LANs are now built using a star topology, making use of Ethernet switches. We have a three-layer network design model. The three-layer model consists of the access layer. This is where our access layer switches live, layer 2 switches, for instance the Cisco 2960s. These provide endpoints and the user directly accesses the network via the access layer. User traffic is initiated at this layer. We have the distribution layer, which makes use of layer 3 switches, or sometimes routers, but generally layer 3 switches. This aggregates the access layers and provides connectivities to services. And then we have the core layer, which uses super high speed, fast switches. This provides connectivity between the distribution layers. At the access layer, you may have switch port security, which looks at the MAC address. At the distribution layer, you will have network layer security, so for instance access control lists, and at the core layer you'll have no security at all because you want to have super high speed switching. Some networks, what they will do is they will collapse the core layer and the distribution layer together to produce what's called a collapsed core. This reduces cost and complexity. Okay, we're nearly there. Common security architectures. So we're looking at firewall design. This is primarily about the device interfaces either permitting or denying traffic based on the source, the destination, and the type of traffic. Some of the designs are simple, just designating an outside interface and an inside interface. A firewall with two interfaces would be configured as follows. Traffic originating from the private network is permitted and it's inspected as it travels toward the public network. The inspected traffic returning from the public network and associated with the traffic that originated in the private network is permitted. So in other words, as the traffic moves out of the private network, it's checked. We check some parameters on that traffic, sequence numbers, etc. And any traffic returning from the public network that is deemed to be return traffic is permitted back through. However, traffic originating from the public network trying to travel to the private network is generally blocked. This is very much how the ASA firewalls, the Adaptive Security Appliance firewalls, work. We specify an inside network and outside network, and then we specify security levels, and traffic can flow from a high security level to a low security level, but not vice versa. A common thing with firewalls is the use of a DMZ, or demilitarized zone. This is a firewall design where there's typically an inside interface connected to the private network, an outside interface connected to the public network, and what's known as a DMZ interface. So traffic initiating from the private network is inspected as it travels toward the public or the DMZ network, and if the traffic is return traffic, then it's permitted. Traffic originating in the DMZ network and travelling to the private network would normally be blocked, but traffic originating from the DMZ and travelling to the public network is selectively permitted based on service requirements. So you may locate your servers in the DMZ network. We can actually configure a Cisco router to act as a sophisticated firewall by making use of what's known as zone-based policy firewalls. In this way, we can actually create zones, an inside zone, an outside zone, DMZ zone, and we can actually configure the routers to allow traffic between certain zones, but not between other zones. Time-wise, we're actually 10 minutes over, so I'm going to have to wind this up. That was the last slide. I think what would be quite interesting would be to actually do a video on how you configure a zone-based firewall. So I might not be able to do it for a week or so, but I will produce a video on how you configure a zone-based firewall, because I think that would be quite useful. And in the meantime, we're not in for 2 weeks. We have a 2-week break. Yes, Sanity returns for a little while. We have a 2-week break. Next Monday, please don't bother tuning in because I won't be here. I'll be somewhere else, and hopefully you will be too. However, in 2 weeks' time, on the 28th of October, at the same time, 2000 hours UK time, you can join us for Chapter 6, Principles of Network Security. I hope you found that useful. Again, we had to cover a huge amount of information. Thanks very much indeed. And Kieran, thanks again. You enjoy your break too. Good luck with the chapters. See if you can catch up if you're a little bit behind, and I'll see you on the 28th of October for Principles of Network Security.